We continue our study of properties of Laplace transforms. In this lecture, we will see the problem of Laplace transform for derivatives of the function. So, our problem will be to relate the Laplace transform of the derivative f prime t with that of f t. So, let me give a terminology before we proceed. So, we will call f will be of exponential order. F is called of exponential order alpha if there exists a constant alpha t naught and m, all positive constants, such that mod of f t is less than or equal to m times e to the alpha t for t greater than or equal to t naught. So, this is just the definition of exponential order that we know, but now we are focusing on the exponent alpha that appears in the right hand side of the inequality. So, we will call the function of exponential order alpha when the alpha is the coefficient next to t in the exponentiation. So, we also assume in the last lecture also we assumed this, that f t is assumed to be of exponential order alpha for some positive alpha, and f t is assumed to be at least piecewise continuous, meaning that it could be continuous as well, but we will not look at functions which are not piecewise continuous, and this will be on the whole interval 0 to infinity. Okay, so our theorem for the derivative. So, this is the derivative theorem for Laplace transforms. And this is that, suppose that f t is continuous on 0 infinity. So, we will assume that f t is continuous on the whole interval, and f prime t exists as a piecewise continuous function on 0 infinity as well. So, first we suppose that f t is continuous, and we also suppose that the derivative itself is piecewise continuous on the whole interval 0 to infinity. Then the Laplace transform of f prime t is equal to s times the Laplace transform of f t minus f of 0. So, in our notation, this is if we denote by gs the Laplace transform of f prime t, and by fs the Laplace transform of f t, then this is the same as saying that gs is sfs minus f0. Now, an important thing to note is that we have assumed f t to be continuous, but we also assume the that ft is of exponential order. This is from our standing assumption that I stated before, but we do not assume that f prime t is of exponential order. So this is an important remark, which is that we do not need to assume that f prime t is of exponential order. So this formula, our formula for the Laplace transform of the derivative, remains valid as long as f is continuous and f prime t exists as a piecewise continuous function on 0 infinity. So even if f prime t is not of exponential order, this formula will still be valid, and in particular the Laplace transform of the derivative will exist even if it is not of exponential order. So for example, let me give an example for a function whose derivative is not of exponential order. So example, this is of a function whose derivative is not of exponential order. So for example, I can take ft to be cosine of e to the power t squared. Now note that this is a bounded function. This is a bounded function because cos is a bounded function. So this ft is a bounded function, and this is we know that a bounded function is of exponential order. Here our bound for ft can be taken to be simply 1, and so ft is of exponential order. But if we take f prime t, this is 2t exponential t square minus sine of exponential t squared. And now we have this exponential of t squared sign out of the sine and cos terms, but this is not of exponential order. We have seen before that this is not of exponential order, and even though t itself is exponential order, this is also exponential order, but even if you multiply a function which is not of exponential order with other functions which are of exponential order, in the end you will still get a function which is not of exponential order. So this function, the derivative is not of exponential order. Yet we will see that the derivative rule, the derivative theorem still applies to such functions, and our formula will be valid. So let's try to prove our formula. So we have that gs, this is the Laplace transform of the derivative. So this is 0 to infinity f prime t exponential minus st dt. Now notice that f prime t is assumed to be piecewise continuous. This is a piecewise continuous function on 0 infinity. So if we take our limit formula for the improper Riemann integral, so this is 0 to r f prime t e to the minus st dt, and so now this is a piecewise continuous function, piecewise continuous on 0 r, and therefore this Riemann integral exists, and now we have to show that this limit also exists. So now we will use integration by parts, and we choose u to be exponential minus st and v to be f prime t. So we will get the limit as r goes to infinity. So now the first term will be, we have to integrate f prime t. So the integral of the f prime t is simply ft, and we have e to the minus st. So the first term is e to the minus st ft from 0 to r minus again from 0 to r, we have to differentiate u. So you will get minus s times e to the minus st, and then integrating again you get ft dt. So this gives you the limit as r tends to infinity. The first term is exponential minus sr fr minus second term is simply f of 0, because e to the minus s times 0 is 1. So this is f of 0, and then you have plus s times 0 to r ft e to the power minus st dt. Now we have assumed that f is of exponential order, so therefore this limit will go to 0. So since f is of exponential order alpha, so I am going to use this coefficient that appears in the right hand side of the inequality in the exponential function. Therefore the limit as r goes to infinity, exponential minus sr fr equals to 0 for all s greater than alpha, because we know that mod of ft is less than or equal to m of e to the power, this is alpha t, for t greater than or equal to t naught. So one can easily see that f mod of fr is less than or equal to e to the power alpha r, and so we will get the limit goes to 0 for s greater than alpha. So therefore our gs is nothing but the limit as r tends to infinity. The first term is minus f of 0, and then the second term is s of integral 0 to r ft e to the minus st dt, and this is nothing but, so the first term is constant in r, so this is minus f of 0 plus s times the limit as r goes to infinity 0 to r ft e to the minus st dt, and now note that this is nothing but fs. So this formula remains valid for s greater than alpha, and so in the end we get sfs minus f of 0 for s greater than alpha. So we get our required formula. Now let us see an example where this formula can be used. So the first example is ft equals hyperbolic sine of at. Now we know that f prime t is nothing but a cos hyperbolic of at, and now we can try to compare the Laplace transforms of each, which we know already, but let's see whether our new formula gives you the same result. So we know that, so let me call the Laplace transform of ft, let the Laplace transform of ft be gs, and let the Laplace transform of ft be fs. Okay, now we know that gs from our computation of the Laplace transform of the hyperbolic cosine function, we know that this is a times s over s squared minus a squared, and we know that f of s is nothing but the Laplace transform of the hyperbolic sine function, and this is nothing but a by s square minus a square. So these are both are valid for s greater than modulus of a. And now let us see whether we have our formula. Let us check that gs equals SFS minus f of 0. So what is f of 0? F of 0 is simply sine hyperbolic of a times 0, and this is sine hyperbolic of 0, and so this is nothing but 0. Okay, and so we are only left with SFS. So on the left hand side we have a times, so this is GS is a times s over s squared minus a square, and this is nothing but a times s times f of s, because f of s is a over s square minus a squared, s square minus a squared. So our formula checks out. So our next example is ft equals sine squared of theta t, and the problem is to compute the Laplace transform of this function. Now we will use that f prime t is 2 theta sine theta t cosine of theta t, which is nothing but theta times sine of 2 theta t. And now we know already what is the Laplace transform of the sine function. So in this case we will use the derivative theorem to compute the Laplace transform of ft. Using that we know already the Laplace transform of f prime t. So by the derivative theorem we have that the Laplace transform of f prime t is s times the Laplace transform of ft minus f of 0, but note that f of 0 is simply 0 because we have the sine squared function, and so we simply have s times L of ft. So the Laplace transform of f of t is 1 over s Laplace transform of f prime of t. Now the Laplace transform of f prime t is nothing but theta times 2 theta over s square plus theta squared. This is the 4 theta squared because we have sine 2 theta here. So this is 2 theta square by s square plus 4 theta square, and this is valid for s positive. Therefore the Laplace transform of f of t is 2 theta square by s times s square plus 4 theta square for s greater than 0. So here we have used that the Laplace transform for the derivative is known, and with by the derivative theorem we can compute the Laplace transform for the function. The next example is to compute the Laplace transform of this function f of t, which is given by this integral 0 to t sine x over x dx. This integral has a special name. This is called the sine integral, and so let us compute the Laplace transform for this sine integral. We will use the fact that f prime t is equal to simply sine t over t. This is by Leibniz rule. For differentiating an integral. So we can use the derivative theorem if we know that the derivative itself is piecewise continuous on 0 infinity. So outside of 0, of course this is a continuous function, but at 0 let's see that the limit as t tends to 0 from the right hand side f prime t, this exists, and this is sine t over t, and if you use see here that both sine of t and t are going to 0. So for example by L'Hopital rule this is the same as t tends to 0 plus cos of t. So you are differentiating both the numerator and denominator. So for the numerator you get cos of t, and so this is just 1. Therefore the limit as t tends to 0 from the right side exists, and so therefore f prime t is piecewise continuous on 0 infinity. So we can use the derivative theorem. So this says that the Laplace transform of f prime of t is equal to s times the Laplace transform of f t minus f of 0, but here again f of 0 is 0 because at when you take the limit as t goes to 0, this is the integral goes to 0 as well. So the integral is in fact a continuous function of t, so this is simply 0. Therefore we get that the Laplace transform of f of t is 1 over s times the Laplace transform of f prime t, and this is valid for s greater than 0. Now remember that we have already computed the Laplace transform of sine t over t, and this was nothing but tan inverse of 1 over s for s greater than 0. So this implies that the Laplace transform for the sine integral is nothing but 1 over s times tan inverse of 1 over s, valid for s greater than 0.